Okay, so I am working today on Lambda, which is the visual programming language project that I've been building. And right now I'm building some test cases that allows for FFI, which is foreign function interface, basically. So what I want to be able to do is I want to be able to define some C++ classes and have them be used by the language. And that means that I have to gather some information about the type that I'm wrapping and using in the language, so that the language can make sense of it. It needs to know things like how many bytes do I need to copy when I move this object around, what functions do I need to call to construct it, do I need to increment or decref it when I make copies, and so on. And so I've built a couple of classes here that capture metadata about the type that's being wrapped, and I want to test that it works, and that's what we're doing right now. So the two classes that I'm wrapping are this instance counter right here, which basically all it does is it just counts how many instances of this class have been, or basically currently alive. And it does this by calling the static function, which has a static variable inside it. It increments that variable when an object is created, and it decrements that variable when the object is destroyed. And I'm going to create some tests that will verify that exactly the same number of objects are destroyed as have been created. That means that every time, basically every time an object is created, it has a finite lifetime. We don't leak any objects, and we don't free any objects before they're finished being used. And that will verify that the language is actually doing its accounting of these objects properly. I've also created another class over here, which will basically count the number of times it's been copied, and that is to ensure that when the language copies these wrapped objects around, it doesn't copy when it's not supposed to, and when it is supposed to copy something, it calls the copy function. So I'll create a few tests that will basically create situations where the wrapped objects have to be copied, and then I'll look at how many copies happened, and I'll verify that it's the number that I have reasoned it should be. So what I'm doing right now, I just made this simplest kind of test case here, which doesn't do anything. All I've done is just declared this wrapped type, putting my C++ types inside this class here. Wrapped basically creates a new class which the language knows about. And that class passes information to the language about the type that's inside of it. So I'm fighting with some compiler errors right now, and let's see what's going on. So right here, inside of this class, mutable.hpp, it's saying there's this error, metadata t is not a class namespace or enumeration. So let's take a look at that. Mutable.hpp, this is basically like a pointer to this wrapped handle type, or sorry, this wrapped type. And what makes it different from a pointer is it also carries a little bit of extra information with it about the type of the thing that it's pointing to. And we need to do that so that we can have runtime dynamic types. So this is like an augmented pointer. It's a pointer with information about basically metadata about the type that it's carrying. And mutable means we can make edits to the thing at the other side of the pointer. It has a corresponding class over here called handle. This is like a const pointer. It allows you to read and look into the object, but it doesn't allow you to change it. Mutable is all of that and inherits from handle, but also lets you make edits. So it says this metadata t type can't be found. It's not a class namespace or enumeration. That's pretty strange, because I'm inheriting from handle right here, and handle of this same class right here defines this type metadata t. Now there's this quirk with template classes where if you don't do anything, actually that that member would not be accessible to the derived class by default, but because I'm using this using statement right here, I basically would expect to have imported that type definition into the namespace of this class so I can just refer to it. So even though this using statement is here, for some reason at this line right here, line 25, right? No, 21. Where is it failing? 21. line 21, it thinks that this is not a type. I don't really follow why that is. I would really expect this to work. It works for other things here, which are not type definitions. This is a constructor, and this is a field. I'm going to comment that out, and I'm just going to recreate. There it is. That's a Copilot for me, filling it out exactly the way I would have written it. Recreate this type right here inside the namespace, and then let's just see what the compiler does here. Unqualified. Okay, well, we did get rid of that error. I don't quite follow why C++ doesn't let me do that. All right, I'm kind of curious, actually. Let's go look it up. C++, inherit, let's call it type def, even though it's not a using statement, but inheriting type defs. Here it is. Defining some type defs. One of them is result type. Yep, doesn't work. Okay, he's not using his using statement though. Well, let's see what the answer says. Type is a dependent type name. It depends on T. That is definitely my situation. Let's go back. I'll show you. So yeah, I'll go to the original definition, which is the same. This contains a T, which is indeed dependent on my template parameter up here. So it is a template type or a dependent type. So if that's true, there's no guarantee that for a given T, there isn't some specialization of base of T, which does not depend, which does not name type. As such, base templates of class templates are not part of the standard name lookup, so you have to qualify it. I guess maybe this is so that it doesn't needlessly try and expand out. Why is that? Or maybe this is so that when it's evaluating the validity of the template before it's actually substituting the template, it can tell whether you made a mistake or not. The thing with C++ templates is that so much of the time it kind of tries to defer substitution, and it sort of doesn't check whether your code is correct until very late. So I'm not quite sure if that's right. Yeah, so I would expect, yeah, look. Or if you prefer, you can simply bring both names into the using declaration. That's what I do. Does anyone complain that that doesn't work? No. I don't get it. Here's this comment saying that the thing that I did should work, and it doesn't work. Getting back over here. Yeah, it doesn't work. Is there a type name? Ah, that's why it is. I got it. It's missing a type name. Here it is. Type name. I bet you this works now. I'm just going to delete that. Let's go back and see if we get that error again. Same error as was before. The original error is gone. Ha ha ha. Fantastic. Figured it out. C++ is really annoying that way. Sometimes you just have to sprinkle this extra little keyword in there for no reason. And if you don't, you get mysterious errors. Curious. All right, so let's continue. Let's keep looking through the errors here. Next one, expected unqualified ID. If const expr metadata t is indirected, const. This const is suspicious. That does not look like it's in the right place. Mutable.hpp 35. Oops, wrong side. 35. Yeah, no, that is not where that keyword goes. It's a brace hanging way out to the side there. It really wants to look like a function opening, but that's an if statement. That's a pretty straightforward typo. All right, I'm confident that error is gone. That was just wrong. Test wrap.cpp error, constraints not satisfied for the template wrapped with t equals instance counter. Because instance counter does not satisfy wrappable, why does it not do that? Because hash if t would be invalid. Ah ha ha. Okay, so this is something for every object in my language, it has to define equality, and it has to define a hash, and this guarantees that every object can be used as a key in a dictionary, which a lot of other objects don't do. In my language, I'm able to do that because all the objects in my language are immutable. So that means you can use one dictionary as a key for another, or a list as a key for, an action. You could use a list as a key for an entry in a dictionary. So in order to wrap an object, it forces you to define a hash function. So let's do that right now. When you're wrapping a C++ type, it asks for a hash function defined in the standard way that you define hash functions in C++, which is you override std_hash. So I'm going to do that right now. Let's see. I'm using namespace Lambda, but I'm not in namespace Lambda, so I can just do this. Template struct std_hash. Okay, so I'm defining a specialization of the struct called hash in the namespace stud. And what this takes is, oh, you're angry. Why are you angry? Argument list for, oh, yes. I need to say how I'm specializing it. So I'm going to say instance counter. And then I think hash return size t. Yes, autopilot knows what I'm up to. Yep. And we don't care about the hash. They're all the same. So this could be any number. Yeah, it might as well be 0xdeadbeef. There. Cool. And we'll do the same thing for the other class. Template. Struct. Yep, you know what I'm up to. Let's give it a different hash. Beef. I don't know what that is, but that will suffice. Okay. I'm also going to require that it defines an equality operator. So let's do that. Bool operator double equals const. They're all equal because they're all the same. And const instance counter reference other. Why are you angry? Explicit type. Maybe you just haven't parsed yet. You haven't parsed yet. Okay. Bool operator double equals, not triple equals, const instance counter other const return true. They're all equal. So they all hash equal and they all compare equal. Whenever you write a hash function and an equality function, usually if you're writing one, you need to have, if you're writing a hash function, you definitely need to have an equality function. And the hash function and the equality function need to agree with each other. So if two things are determined to be equal, then they better have the same hash. You can't guarantee the reverse though, of course, right? Because there are only so many hashes, but you can have way more objects than there are hashes, right? There's only like 2 to the 64, this is on a 64-bit system, 2 to the 64 different hashes that you can return, but if your objects are big enough, you could return way more than 2 to the 64 different kinds of objects. So, and that's just the nature of hash. It's not one-to-one and onto. Cool. Okay, so both of these have hash functions. Both of them have equality operators. This is still angry. Why is it angry? Template not satisfied. Okay, well let's get more detail. Let's try and compile again. By the way, when I do this bunch of enters, I'm trying to separate my previous errors from my current errors, so they don't mush together and I don't get confused about what errors are current. This is just like a muscle habit that I do that. Okay. Mutable, no member named value in indirect payload. Okay, I think I have a sense of what that is. Use of undeclared identifier value. Use of undeclared identifier deck. Okay, this is an easy one to fix. Mutable 46. Mutable 46. Okay, this is that same dependent type name thing where the methods from my base class don't show up in the namespace of my derived class because there might be, sort of like that Stack Overflow answer was saying, this might be specialized in an arbitrary way for whatever t we're substituting. So there's really no way to know what objects, what methods, what members you will find on this class before you substitute t. So it doesn't search those things. But we can say we expect to find deck on ourselves by doing this. I could also do a using statement, but I only use deck in one place here, so I'll just explicitly say that deck is something that we expect to belong to this object. Okay, cool. So that one's fixed. Let's go to 39. No member name value. Okay, so 39 right here. Indirect payload. Okay, so indirect payload, this is a class that I've created, which is just the thing. It's like a shared pointer, basically. It's the thing that lives on the other side of this pointer. And it keeps a ref count, and then it keeps the body of the object. And this is just a thing that allows me to pass around pointers to the class that I'm wrapping. Why did it open dictionary? That's weird. Go away. You can kind of think of it as like a vector with only one element in it. But let's go look at what this is. And yeah, so here it is. This is a thing that has a ref count and a payload. And I dynamically decide how big the payload is. Basically, I do malloc with the size of this plus however much stuff I want in the payload. This thing, this max align t, this is the maximum alignment for any type in C++. So some objects have to be aligned with certain byte boundaries because of the types that are inside of them. And this is the biggest possible alignment, so it ensures whatever kind of object you're storing in your payload, it is guaranteed to be aligned along that byte boundary. So by putting this aligner in there, that ensures this union sort of pushes this data up against the widest possible byte boundary. So yeah, I think I was referring to that as value. Yep, instead of payload. Is that right? 3961. Let's go back over here. No. Oh, I really hate the tab system. Here we go. Interpret cast. New object. Direct payload. Yeah, I don't think value should be there at all. And is it, let's get rid of this and this. Underbar payload. That should work. Right? Yes. Okay. Let's just verify that those errors have gone away. Indeed they have. Constraints not satisfied. Invalid operands. All right, I'll come back to that one. Let's solve this one. 41, use of undeclared identifier value. What did I mean by this? 41. Is this something that lives on handle? Oh, what did I mean? What did I mean by that? This is, looks like this is supposed to return a reference to the existing object. What do I call that? I think I call that body. So let's try that. I'm going to dereference body. And did I call that underbar body or just body? Just body. So this is going to return, yeah, a pointer to the actual object that we're wrapping. I'm going to dereference it to just get a reference. And then I'm going to construct a new object of the wrap type in place using the old object. Yeah, I think that should work. So now we should be down to one error. Let's see what we get. Yes, okay. Invalid operands to binary construction. Or binary expression. What do we have here? Okay, so I'm defining this concept. I'm using C++20 concepts here to restrict the type of object that can be wrapped. And so I'm putting sort of constraints on the kinds of things that you can substitute in here to make sure that basically my code can support whatever features the wrapped class implements in terms of things like equality operators and copy construction and all of those sort of things. This is the same thing that was requiring me to implement a hash function and a comparison function. And it looks like it's angry about how the comparison function is being evaluated. One thing I don't get is I don't get why, if these two things are pointers, why don't these evaluate to references? Let's look at where I define that concept. Yeah. So, yeah. What is it using for T? Copy constructible. Yeah, so this doesn't have any like reference qualifiers on it or anything like that. Be invalid operands to binary. All right, let's look at the definition. Ah, haha, there it is. I did not change the argument type. This needs to take another instance of itself, not some other random object. That's it. That's what the problem was. So there it is. My concept helped me out. It caught an issue where this class did not have required support. So, and it told me why. Let's try again. All right, my test passed. All right, so now that the test is passing, I want to actually check that things are behaving properly, because this is my test, and I would hope that passes. So in my other test modules, I've had this function here, test type expectations, and yeah, so this is just actually verifying, in the other modules, this verifies that the metadata for the type that we're talking about, whoa, calm down there, autopilot, goodness. The metadata for the type that's being tested kind of matches expectations. Let me show you some of the things that I would want to check. Base, yeah, here we go. So every type in the language has this kind of object associated with it called an ABI info. And this encodes all kinds of stuff like what type category is it? And there are some major categories here like a buffer, which is like an array, basically a list, an associative map, some type, which is like a union, a product, which is like a struct, all that kind of stuff. So it carries which kind of object is that. It tells you whether it's ref counted. It tells you how many bytes it requires to store. It stores a unique type ID for objects that are uniquely typed. And more information. These are functions for constructing, comparing, hashing, and then detailed type information for each of those subtypes. So every kind of type that the language can handle, it has one of these things associated with it. So when the language encounters a bunch of bytes, it knows what to do with those bytes. This should be verifying our expectations for what that metadata is. And in particular right now I'm testing C++ wrappers. So there's actually kind of a corresponding object on the C++ side. That's kind of not this free-floating little struct. It's a class of its own that's templated. And that actually allows us to get all of this data here, which is stored in a structure and passed around inside the language, actually as statically available, compile time available information that the compiler can then optimize away when it's compiling code that manipulates language objects. So that should make it more efficient to write C++ code that handles these language objects. So the templated class that's sort of the static mirror image of this ABI info, I've been calling ABI metadata. And that knows similar things. It knows about whether the information is available at compile time or not. It knows whether the layout is known at compile time or not. Those are not exactly the same thing. I could go into detail, but not right now. It knows how many bytes it takes to store, what its alignment is, and a few other things. So let's look at the ABI metadata for the wrapped type and kind of come up with some assumptions that we want to check. So for objects that are small enough, we want to pass those objects around directly because they're really lightweight. We don't want to wrap them in pointers. We just want to store the object directly. There are a few conditions for whether we do that or not. That's encoded here in this function is indirected. And basically, if the size is small enough, then it will not be indirected. Indirected means stored by pointer instead of by value. So if it's too big, we don't want to copy zillions of bytes every time we move an object from one place to another. We just want to copy a pointer. This also allows it to fit inside of lists, which have a maximum size that they can store inside their leaves. And then also we require that it's trivially copyable. So I kind of want to test that. Neither of these, this one should satisfy it, right? This one should satisfy it. So let's test that. Let's see if ABI metadata of wrapped, actually I define it right here, wrapped counter is indirected. And we'll do expect false on that. All right, that's simple enough. Let's see what happens. Even a simple thing can fail. Which it has failed. It thinks it's indirected. Why does it think it's indirected? Let's just, it's not too big because it's a tiny little object, so it's got to be the other thing. Trivial. Say std is trivially copyable. B, just needs to take the value of wrapped counter. Yeah, okay. I was going to say no, almost certainly. Let's just verify that. Verify your expectations. That's what we're doing. What? It says it is trivial. It's indirected if it's greater than max field. Why? How is this possibly? This is like a stupid bit flip in my brain somewhere. It's got to be. Expect that it's not indirected. It is indirected if it's too big. And it is indirected if it's not trivially copyable. This says it is trivially copyable. Here. What is going on? All right. Tell me the size. Too big? No, size of. Wrapped. Oh, no. Yeah, no. What do we call this? Not wrapped counter. It is instance counter. Counter. Because that is the inner thing, not the outer thing. Wrapped counter. Come on. I don't know. Just, all right, fine. I was hoping autopilot would do that work for me. I did not fill out that statement the way I wanted to. Well, it says the size is 1. So that's not too big. What is the max field size? Well, actually, this should just tell me. I hover over it. Okay, it's an expression. Just verify. I feel like before I do my thinking, I just want to do some looking. Just make sure all the values are what I think they are. So it is not trivial. I shouldn't call this too big. I should just say size. Size. So I don't confuse myself. And the max field size is more than 256 bytes. It's very big, so size of t should not be bigger than this. It's indirected. This is false. This is true. This is false, so neither of them is true, so the whole thing is false, and yet true. I'm so confused. I'm going to pause while I think about this. Okay, can you see the error? I found the error. Or at least there's one discrepancy here, which is I'm asking, is trivially copyable of wrapped counter? But wrapped counter is a wrapper around the thing that I actually care about. It's the inner thing. So I need to ask it if instance counter is trivially copyable. So I bet this explains the discrepancy. Now let's see what happens. Trivial 0. What is not, why is it not trivially copyable? I guess the constructor isn't trivial. Maybe I need finer grained tests. Let's look up what trivially copyable actually entails. All right. Trivially copyable type. Okay, so this is just a link to this concept right now. Okay, trivially copyable scalar. It's not scalar. Trivially copyable class types, arrays, CV qualified versions. Okay, what's a trivial? Trivially copyable class has at least one eligible copy constructor, move constructor, copy assignment, or move assignment. Oh, I think because okay, this is C++ weirdness. Because I have defined this constructor, I think the other default constructors are no longer automatically present. So to bring them back, I want to do this. Instance counter, if I can spell it. Const, but I can't. Trivially copyable. So if I, if I define this copy constructor this way, then it's no longer trivial because it's not just copying the bytes, it's doing something when it copies the bytes. If I make it the default, then it becomes trivial, but then this no longer counts the number of live objects. But I think that's okay, because in our tests we know when this circumstance will come about, and when we're checking how many live instances we expect to find, we should account for the fact that any objects which have been copied will not have incremented the count. We'll see if this gets us into hot water. I'll also do the same thing for the move constructor. And let's do move assignment. Instance counter. Yep. And same thing. I like to have all of my stuff vertically aligned. It just makes it just feels tighter, but it also makes things easier to read. There aren't as many examples of that. Here, this is a great example of that. Side tangent. I really like making equal signs line up and just having gap in between to make everything line up, because then it looks like a table. You have the variable that's being assigned on one side and you have the value on the other. These are all the values all nicely lined up. These are all the variables all nicely lined up. And if you have things that correspond to each other, like this kind of stuff, you can also see if you misspelled something because they're lined up. It'll show you if something isn't the way it's supposed to be. So if these were both, you know, if I forgot to change Cedar to Dieter or something like that, having these next to each other would show me the discrepancy because they're visually lined up in my field. If they were, whoops, let's go back here. If they were sort of not lined up, is it like this? You might not see because this sort of, it doesn't invite the visual comparison here. They're not vertically aligned. So I really like having everything aligned. End side tangent. Where was I? Copy constructors. Yeah. So whenever you define a copy constructor, you usually want to also make sure there's a copy assignment, and same thing for move constructor and move assignment. And I've done that here. Copy constructible, yes. And I haven't done that here. And we will not make this the default, so we want to make it non-trivial. And we will pick 1. So this will tell us how many copies we've made. Got it. All right. Let's see if it passes now. Non-void function does not return a value. Still failed. Not trivial. Okay, we got a couple problems here. That's our default. This, yeah, so return this. We got to return a reference to ourselves. That's all fine. Now, why is it not trivial? Default copy assignment, default move assignment, sorry, construction assignment. What is your problem? What are you angry about? All right, let's go back to this. At least one eligible copy constructor, move constructor, copy assignment operator, remove. I have all of those. Each eligible copy constructor is trivial. All right, what do you mean by that? Trivial copy constructor is not user provided. It's defaulted. All of the following must be true. Has no virtual member functions. There's no virtual base class. It does not. Let me show that to you. Yeah, we don't inherit from anything. Nothing is virtual. Not even my destructor is virtual. Copy constructor selected for every direct base. We have no bases. Copy constructor selected for every non-static class type is trivial. Every non-static class type. Member. Okay, we have no members. We have no non-static members. This is kind of a static member. Why are you upset? I kind of wish that it would give me more information about why this is not satisfied. I wonder if I can get that. I think if there's a concept for this, I could plug it into a concept, and then hopefully the concept mismatch error will help me diagnose what aspect is not matching trivial construction. Actually, did I finish reading everything? Let's finish reading everything here. Copy constructors. Where am I? Oh God. Trivially copyable. Trivially copyable class types. Copy constructor is trivial. Move constructor is trivial. Assignment is trivial. Move assignment is trivial. Is a non-deleted trivial destructor. And destructor is not trivial. That's why it's angry. That's easier than writing a bunch of code to figure out why it's not matching. Reading is good for you. Again, with the dictionary, go away. I need to turn that off. I feel like that's like a triple click Mac thing or something. Nobody asked for that. But I want that. Okay, I'm just gonna make a totally trivial class. We'll test each of these things independently. This thing is sort of constructed to test how many instances of it are alive So we'll do that. We'll let it do that to the full extent of the law. And then we'll make a separate thing that will just test that it can sort of trivially copy objects around. Cool. So we'll make it behave properly. This one, because we're moving, I think we actually still want to do this. You would think no, because we're like transferring ownership of the other object. But that's not true, because when a move constructor is called, the other object stays alive until it goes out of scope. So let me show you what I mean here. So, oh my god, with the dictionary, always. All right, so here's our function scope, and here's my class C, and I'm calling some function which let's actually do this. My class D stood. We're going to construct it with C. So we're basically transferring ownership of C to D. And then I have, more stuff in here, more code, yada, 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 and then we return. So you would think that C dies here when it's transferred to D, but that's not actually true. C remains live until it goes out of scope at the return statement down here. So when you implement a move constructor, what you actually have to do is you have to put the other object in a valid state so that when its destructors eventually run, it will do something sensible. So until basically if let's run through this. In this function, I'm constructing a new object. So that's like this class right here, or this statement right here. D has become alive. Why? Why is this happening? Is it like a command click? Why? Okay, D is alive here. Here only C is alive. When C became alive, it incremented its counter. When D became alive, now we want to increment its counter in here as well. But C is still alive until down here. It just, has given its contents to D, whatever that means. And when C gets to the end of the function, when it gets to the return statement, it's going to run its destructor here, and it's going to decrement again. So, and then whenever D goes out of scope, which is also down here, it's also going to run its destructor. So both of these objects, C and D, are going to run their destructor. So we need to run the inc function the same number of times. We need to run it here, and we need to run it here, which means we need to run it inside of our move constructor. So that's the logic behind it. All of our constructors need to have this increment. Cool. And in this case, actually, we don't do anything because this object remains live and the current object remains live, so we don't change anything. And similar logic here. So I think this actually does what we want. This should actually tell us the number of live objects. Okay, so let's make a trivial object. Trivial. Okay. And X. Let's have the constructor not be trivial, because I want it to be possible to construct an object. Brain fart. I want it to be able to initialize an object without having to basically make it into this indirect pointer object. I want to have small objects that can initialize themselves without requiring them to be memory allocated. So let's do something here. And trivial consts no equals defaults, and defaults This is what Copilot is really great for. So this guy actually should be trivial. Now we have all of our classes that we can test with. Using wrapped trivial equals. There we go. So let's try this. Get rid of all of our debugging garbage. Wrapped trivial. So far we're learning that we haven't actually done anything wrong here. Our code has told us only correct things. What I'm learning is more about what the requirements of my library actually are. Why are you angry? Template constraint not satisfied. Oh, darn it. Okay, well, let's get some more detail about this. Tell me, why not? Constraints not satisfied. Trivial does not satisfy. Wrappable. Because hash function, of course. It's all right. You can copy paste this bad boy right here. Trivial. What kind of hexadecimal nonsense do we want to put in here? Feed bead. All right. Now are you happy? Yes, you're happy. No, you're not happy. This constraint still not satisfied. All right. Tell me. Tell me why. As the Backstreet Boys would say, trivial does not satisfy wrappable. Oh, this has to match as well. That would help. Once again, got all these wonderful errors we're catching. Constraints not satisfied. Oh, you need a comparison operator. Fair. Bool. Operator equals. No, you had to do that right. Good. How about now? All right, that took way too much time. Okay, one more thing. So I lied to you before. I said that because I defined this constructor, these default assignment and construction operators go away. There are situations where that's true, but this isn't one of them. If I get rid of these, actually, it still works. Actually, I need to compile this, but yeah, run the test again, please. Yeah, still works. So I don't need to be so verbose. These things exist by default. All right. One more thing. I broke my own rule. Remember that moment when I was waxing poetic about how the comparison operator and the hash function have to match? Well, look at my comparison operator and look at my hash function. That is not good at all. Yeah, so this is a situation where two things could be exactly equal. Actually, I guess this is technically correct. They're equal, and they do return the same hash function, but also all objects collide. That's not a particularly good hash function. It's a valid hash function, but it's just about the worst hash function that you can have. So I'm going to do something slightly better and return the value inside of it. So now, oops, I should give this a name. Trivial. Now our hash function tells us something about whether the objects are equal or not. So that's a little better. All right, let's keep going. Let's see if we can validate more things about our classes. We have one test, which is returning what we expect. It's passing, but what else can we check? We're expecting this to be false, so the size of this guy should also be the same as the size of the class that we're wrapping. So expect EQ, size of trivial should be equal to size of wrapped trivial. Yeah, you know what I'm talking about, Copilot. And let's also just kind of check that our ABI metadata knows that. So let's do expect EQ, size of wrapped trivial is equal to ABI metadata. So this is the class that statically tells us all the properties of the type that we're talking about. Again, Copilot knows exactly what I'm getting at, so that should be true as well. What else can we ask? I'm not even looking in the right place here. What kinds of things can we get? Expect true. Let's say has static layout. That should be true. Every so often my fingers touch the wrong key and my whole screen changes to something different like that. And it's very disorienting. Cool. What else is important? Static layout. Oops. This is static ABI. That just means that we don't have to provide that runtime ABI info. So we don't actually have to store it with the object. It can be a global variable somewhere, and then we can pass the objects around by themselves. Most things that I've been dealing with satisfies this. This is pretty important for efficiency, so I just want to check that that's true. Size of line. If it gets the size right, it's going to get a line right. I don't care about testing every last little thing. Anything else? I guess let's do this for all the other types. Let's verify our expectations. So because copy constructible is non-trivial, we expect it to be indirected. So we're going to expect this counter. We'll do this counter. Yeah, actually, sorry. We'll be oh boy, that did not select what I wanted it to. Let's try that again. Counter, instance counter. Cool. Okay, so this is the one we expect to be indirected because we tried it and it turned out it is indirected. And we reasoned through it, so we believe that's the correct thing to do. These sizes should still match. It should still be static, and it should still have static layout, should still have static ABI. What static layout means is that the size of the object is known at runtime. There are things that might not be true for, like you can actually have runtime defined tuples where you don't know how many elements are in the tuple until runtime. Or you can have like an any object that has a completely unknown type, and you don't know what type of object you're holding until you basically get one of these little ABI info objects that tells you what type of object you're holding. That's a case where the layout won't be known. But that should not be the case for any of these. And let's do this again for the last type, which is, we did wrap trivial, we did wrapped counter. Let's do this, let's make these in the same order so it's easy to read. The copyable will be, if I can talk, copyable. This guy will be indirected. Copy constructible. Copyable. Okay. And Copilot gave us one too many braces, so we'll get rid of that. Are you going to stop being angry? Yes, you will. What do we get? I need to compile. How are we doing? Failed. Copy constructible. Expected equality of these values. Ah. Yeah, actually, you know, that's, this is correct. Oops. So once again, my code is correct and my test is incorrect. So for things that are indirected, the stored size of the object, basically the wrapped object, is not going to be the size of the object, because the wrapped object is actually just storing a pointer to that, what is it, that thing that we saw before? What did we call it? indirect payload, basically, that little one element vector. We're storing a pointer. So actually the size of instance counter should be the size of void star. But the size of this guy and the size of that guy, these should agree. These are talking about the same thing. But we'll make this say the right thing. So code is correct, tests are incorrect, but it's good to know. Let's try again. Size of instance counter. Did I change the wrong one? I did change the wrong one. That's annoying. Size of wrapped counter should be the size of wrapped copyable should be the size of void star. Again. There we go. All right. We'll call that our type expectation satisfied. Okay. Now we want to actually test that these objects behave the way that we expect. All we've done so far is just detect that our metadata about these types that we're wrapping is correct. Let's test the behavior of the objects. So let's start with the simplest thing first. Let's do our wrap trivial type. So I'll define a new test. And oh my goodness, Copilot has gone absolutely bonkers. Let's get rid of that. I did get the header though for free. Was it worth it? Verify handle expectation. Let's just let's say we're verifying the trivial type. Verify trivial wrapped type. Okay. So what can we check? Let's see. The wrap type has a value. So the way that in C++, the way you store a language objects is you wrap it in a value type. I have this type value right here. This is a thing that can hold the actual bytes of the object. And if those bytes, if the meaning of those bytes is not known until runtime, because, for example, it's holding a runtime type, then the value also holds the metadata and the ABI info object for the bytes that you're holding. So it holds a value and possibly holds metadata about the value if it's needed and it's not available at compile time. So the way that would look is I would just declare a value of wrapped trivial. And this should compile. So far it's looking, yeah, okay, that compiles. And then I think that we can test that it was successfully constructed. So I want to test that this is like a language object or a wrapper around a language object. I want to test that the language object ran the C++ constructor so that when this object is constructed in the language, it does exactly what it would do when it's constructed in C++. So in this case, we construct it with a value 1, 2, 3, 4. So let's look into this object and confirm that it contains the value 1, 2, 3, 4. So in value, the way that we do that is we borrow a pointer to it. That's this function right here. And that constructs one of these guys, a handle, which is, again, that pointer object which carries metadata about the thing, or possibly carries metadata about the thing that it's pointing to. So this is a annotated pointer. So we'll do a handle of wrapped trivial, if I can spell trivial, val pointer equals val.borrow. That should compile. So far, no complaints. Actually, Copilot, what were you suggesting? Expected Q, val pointer. Ah, yes, I can't do this, sadly, though. I want to get the contents, which is this function value. Oh, I was referring to that before. If I had put this arrow before value inside of mutable where I did this business, that would have fixed it with a little less work. Oh well, value. So what I should do, I should be able to do this. Dot value. That should give me a reference to the contained object, and I should expect that to be 1, 2, 3, 4. And that compiles. So let's see how far we got. Oh goodness, lots and lots and lots of errors. Okay, what's it mad about? No matching function to a call to operator new. Ah, because my object is not default what? No. New object value. ABI 102. Let's take a look. Let's just see if we can figure it out. ABI 102. So what kind of an object is this? I would expect that to be a T. The inner type, basically. I think I just need to static cast this. So, is that true? Why do I need to static cast it? I would expect that this should be a T. If it's indirected, we're going to get a pointer to an indirect payload. Size of T, if it's too big or it's not trivial, then we store a pointer. Otherwise, we store the object directly. So this should be a T. It should be a pointer to a T. There we go. We just need an addressive operator. This is placement new, by the way. So I can basically construct an object on a particular piece of memory that I pass to this operator, as opposed to getting it from the heap. It's sort of slightly esoteric thing, but I'm basically saying this is a pointer, and I want you to run the constructor on the memory in that pointer. Assume there's no live object underneath it. This is how things like std_vector can construct new objects in the sort of empty space of their memory buffer. And that's what we're doing here. Let's see if this gets us further. Many fewer errors. By the way, just sort of like sanity technique for dealing with this huge number of errors is I ignore all the garbage. I don't try and understand all of this stuff. I just visually start at the error itself. And then I assume all of this stuff is often irrelevant detail. But if this doesn't make sense, then I start reading from the kind of simpler to uglier stuff. And usually something close to the error will tell me about what's going on. Either at the very bottom, which is basically like what's asking for the error, or near the very top, which is what's happening right around the error. But I ignore all of this stuff until I need more info. I just try and make sense just from this. Really important kind of error bushwhacking technique, because this is just, information overload. All right, what do we got here? Handle.hpp, no viable conversion from returned value type storage T, aka trivial, to const trivial. I think this is also missing. Yeah, we are supposed to return a pointer, and we're returning by value. What line was that? That was in handle 29. 29. I'm not in handle. Let's go and try this again. 29. Yeah. So this is actual bare object itself. So we need to return a pointer to that. So we'll just do addressive operator. And let's look at this one. Let's see what's going on here. Invalid operands to binary expression. Const trivial, const int. So this is, why don't we do this? I could do two things. I could construct a trivial around this and compare the two trivial objects, or I can compare the inner value. But actually, I can't do that because I haven't made a constructor around int on my trivial object. I've just made a default constructor. So we'll do the first thing. We'll do .x here, and we'll delete this nonsense. I bet this will work now. Let's have a look. Yay, all right. Now we have two passing tests. Fantastic. What else can we do here? There's not a lot. You just put it inside a container and verify that it contains it. Indeed it does. Let's try and edit it. So let's do val.edit. So this is as opposed to borrowing, which just gives me a immutable view into the object. This actually makes sure the this gives me a non-const pointer, basically. And Copilot knows exactly what I'm doing. Yes. Does it work that way? Let's have a look. It's angry. Yeah, that should work. What are you upset about? Isn't that right? This should return a T, not a wrapped T. I have to do this twice. Here, this is giving me a mutable pointer from value. That's this. And then from my mutable pointer, I want to express my intent to actually edit it. So I have to edit twice. This is kind of clunky. I don't like this. But the reason why it does this is because of the case where this is actually indirected. When we make changes to an object, because it's immutable, we have to do a copy on write. So let's say I make a zillion copies of this value, as opposed to copying all of the bytes of that value all over the place, in the case where it's large and indirected. Instead, it's going to copy a bunch of pointers to the same object that's going to be shared among all of them. But it's an important property of my language that there are no side effects. So let's say one of those pointers gets passed into a function, and that function edits the value that it's pointing to, then all the other pieces of code, all the other data structures that have references to that shared object are now going to see the new value, and that's a side effect. And in my language, basically all the values need to behave as though they're immutable, and this violates that. So what we do instead is, when that one function that's making an edit tries to edit something that's shared, it can basically look at the ref count inside of this indirect payload here. If there it is. It can see if there are other pieces of code. It can see if this ref count is larger than 1, which basically tells it there are other data structures or there are other threads that have a view into that same data, if that number is larger than 1. And if it is, then it makes a copy of the entire payload for itself that only it can see, and then it edits that payload. So we want to be sure that when we do that copy, we're actually doing that because we're about to change the contents, not just looking at them, which is why we actually express edit here. This is the action that causes the copy on write. We don't really want to do it here, just at the moment when we're getting a mutable pointer. That doesn't necessarily mean that we know we're going to edit. We want to express the intent to copy on write right here, because that's a potentially expensive operation. So did I test this? That was a long rambling. I think I did. No, I didn't. No viable conversion from returned value of type storage trivial to trivial star. Once again, forgot which line of code was that? Mutable 28. Mutable 28. Same thing. I forgot to take the address of. I expect this to pass. And it passes. So that's my trivial test. Good. All right, so let's keep going. We were just talking about this copy on write behavior for indirected objects. So let's actually check that this is working. We'll do the next version of this, but instead of for our trivial wrap type, which is basically just storing the bare bytes to the thing, let's try it with our wrapped counter and do something similar. Verify that when we're storing a pointer instead of the bare bytes, it still does the right thing. So let's do test, object name, wrap type, right? Copilot doing a little better this time. Keep going, you got it, little buddy. Wrapped counter. Good. Let's close this off so it's not so angry. And same thing. Actually, we want to check the value inside. So this currently has no members. Let's fix that. Let's give it a member. We'll call it X again. And I suspect we're going to want to do the same thing here as well. Shall we also, yeah, 432. Make the numbers different, just so there's no accidental collision. I don't know if any of the tests might confuse one thing for the other. This would expose that if I did that. And this, now these things are no longer the same. Oops, X, other.x, same thing. Again, I don't need to type that twice. Constructible. All right, we'll deal with that in a second. How far down this road do I want to go? When we're copying, we need to take the value from the other guy. And when we're moving, and let's just sort of play act invalidating the other object. Actually, let's try and do this. 0x, 2, 3, 4, 5, 6, 7, 8. This is easier to detect if that value winds up in a place where it's not supposed to be, because zeros show up all over the place in memory, even when you don't touch that memory. Okay, so now we've given this instance counter, we've given it an X variable. We transfer these default guys here. That will automatically copy my member variable, which is plain old data, so I don't think I have to do anything there. And then this no longer makes sense. Goodbye, dead beef. We'll do the same thing that we do in all the other places. All right, looking good. Yeah, let's we can't do that. Let's have this, let's have them all have a non-trivial constructor. Why are you upset? Oh, you just didn't parse. Okay. Am I forgetting anything? I imagine my very pedantic code checks will tell me if I'm forgetting something. I am forgetting something. Other. Okay. Same thing here. Oh, this is an assignment operator, not a constructor. I'm confusing myself. I'll come back to that. Let's see here. This we actually do need to steal the value. Okay. So in this case, this is copy assignment. Right. I'm confusing it for instance counter versus this is counting the number of copies. So yes, we actually do want to increment this. I was confusing these two things. Okay, now am I forgetting anything? I don't think so. Let's go back over here. All right. Expect EQ. Is that right? Yeah, that's the right value. Copilot can be pretty clever sometimes. All right, let's just check that. We made a few changes there, plenty of opportunities for screw-ups. And there's one right there. No member named payload in indirect payload. Yeah, I think that's missing an underscore is my guess. Let's take a look back over here. Indirect payload. Indeed, it has an underscore. What line of code was that? That was ABI HPP in wrap 97. ABI HPP in wrap 97. There, value payload. Where object is wrap t, object value. I think that's correct. Let's try it. There we go, it passes. All right, let's try editing the guy. Let's make a copy. And I think, if I recall correctly, I can do this. Let me take a look. This will copy. Image type. Indeed, it will. Oh, and I might want to close that template parameter. Looking good. Okay. So now this guy should contain the same value as that guy. Let's actually put something fresh in there so we know the difference between this being copied and constructed anew. So let's do a simple edit first. We'll do a bunch of 9s. And now let's check that, well, first let's check that edit actually succeeded. Now this guy should also have a bunch of 9s in it, not 5432, so let's check that. Let's do val2.borrow. Well, I can't do that, Copilot, that's not allowed. Actually, let's do expect eq dot x is equal to 4 9s. Okay, let's oh, you're upset. Ah, right, yeah, should be okay now. Please parse. Maybe you're not okay. Let's get more detail there. Undeclared use of vatu. I feel you, buddy. Indeed, that's wrong. Now are you happy? Yes, now you're happy. All right. Do you pass? And it passes. Fantastic. Okay, so now let's test the last thing. We're going to edit one thing. Right now, these share memory because that should be what happened when I moved this guy into that guy. And actually, is this the class? This counts how many actual instances we have. So I should be able to. There should basically be only one instance right now because these guys are pointing to the same object. They both have pointers to one object. So I should expect, what do we call it? Instance counter. Dot. Yep, that is exactly what I wanted. It should be 1 because they're sharing their types. Why type name is not allowed? Is this a like macro expansion problem? What's going on? Okay, I need a better error, which this editor is not going to give me. Instance counter does not refer to a value. I guess, oh, yeah, that's what you need. Python lets you do that. I have Python brain. All right, let's try. This J8, by the way, is for both sconce, which is the build system that I'm using, and makefile, which is really common. -J allows you to give a number of threads. So this says, build my project with eight cores, or with 8 threads. Right now, I'm basically only building one file at a time, so it doesn't really matter, but I kind of have that setting there by default for when it needs to rebuild a lot of stuff. And everything's passing. So far, so good. That means my little instance counter is doing what I expect. And does it start from 0? Yes, it does. That's not the default value. Once we get to the end of this, I'm going to go back and sort of comment all of this stuff. Actually, let's do that right now. Both objects are shared by 2 pointers. Val2. All right, so now let's edit the second guy. Bunch of ones. No, that's the opposite of what I want. This should be 4 nines. Val2. So the one that I just edited should have all the ones, and the ones that I did not edit should have all nines. And lastly, there should now be 2 separate instances. And that all worked. I think that's pretty successful. Let me show you one thing that's going on here. Like, what does this inc0 mean? I'm doing a little trick here, which I've just found really convenient with static variables, is to wrap my static variables inside a static function. And C++ really helps you out in kind of a nice way here, which is that when your static variable is inside a function, the initialization statement does not happen until the first time the function is run. And then ever after that, the function is just used. It's not, or sorry, the static variable is just used. It's not reinitialized. And it also does that in a thread-safe way. So these are some really slick features, actually. It may be one of the most subtle, annoying things that it solves is if I were to declare a static variable inside the class itself, I also have to initialize that thing in a C++ file somewhere like this. That's going to be int instance counter static var equals 0. So I have to initialize it out there. And I have to take care to basically not initialize it in more than one translation unit. That's basically a translation unit is a C++ file and all the headers that it includes. So if I were to do this in a header somewhere and then multiple C++ files were to include that header, then that variable might actually be initialized twice, which is an error. But even worse is if there's some expression which initializes this guy, when that expression actually runs is undefined. And this causes all kinds of problems. This is actually a deep problem that I had to fight elsewhere in my library, which is that I have a bunch of global variables which are initialized by functions, and those functions depend on other global variables. And whether or not those variables are initialized at the time the function runs is just completely undecided. So static global variables are bad because of that problem. They're really hard to reason about. When I stick them inside a function, you don't have to worry. The variable is initialized when you call the function, whenever that is. So when you need the value, C++ guarantees that it's available for you. And you don't have to do that annoying sort of separate initialization statement elsewhere. So the variable lives inside the function, which means I need to be able to both set the value and access the value with a call to that function. So I've added this variable here, which is how much I want to increment or decrement by, and then whatever the result is, I change back. So if I want to increment it, I pass the value and discard the result. If I want to read it, I pass 0 and read the result, which is what I'm doing down here. So that is a way to both change or access the variable which lives inside that function. I couldn't write a separate function which accesses that variable because it's a separate function. It can't see what's inside this guy. You know, static. Yeah, you get the idea, right? Like, how would I, what would I return in here that lets me see the value of this guy? So it has to be encapsulated in one statement. But that's just a little tricky thing. I found it very useful to have these global variables. So yeah. All right. Well, I think this is probably a good stopping point for today. This is an experiment. I have no idea if anyone will find this interesting or not, but I'm making this one way or another. And thanks for coming along for the ride. And if this video gets any likes or interests, I'll keep posting. I'll see you next time.